If A and B are two non-collinear vectors, then show that the points having the position vectors, these two position vectors, are collinear if the determinant value equals to 0. Okay, let us begin. Now, what we'll do, to understand this problem, we're going to consider 3 points A, B, and C. And also, we're going to consider another point O, which is going to be a origin of some coordinate system. Now, with respect to this origin, we can define the position vector of point A, point B, and point C. So let us suppose that the position vector of point A, it's a directed line segment going from point O to point A. This will be equals to L1A vector plus M1A B vector. Then OB vector, this is going to be the position vector of point B, so that's defined by L2A vector plus M2B vector. And we have the position vector of point C defined by L3A vector plus M3B vector. Fine. Then, assuming that these 3 points A, B, C are collinear, that means if we draw a straight line, these 3 lines are going to lie on this line. So, assuming A, B, C are collinear, there exist 3 scalars. Let those scalars be denoted by X, Y, and Z, such that X times OA vector added to Y times OB vector plus Z times OC vector, the sum will be equals to the null vector. This is a theorem we have already discussed about it, where the sum of these constants, these scalars, x plus y plus z, that will be equals to 0. Now let's substitute the value of OA vector with L1A vector plus M1B vector. That will be added to y times OB vector. The OB vector is L2A vector plus M2B vector added to z times OC vector. The OC vector will be L3A vector plus M3B vector, and that will be equals to the null vector. Furthermore, we can simplify it to get x times L1 plus y times L2 plus z times L3 all multiplied to the vector A. Added to, we have x times M1 plus y times M2 plus z times M3 whole multiplied to vector B equals to the null vector. Now in the problem, it's already mentioned that A and B are two non-collinear vectors. Now since A vector and B vector are non-collinear vectors, if they're non-collinear, then it simply means that x times L1 plus y times L2 plus z times L3, this must be equals to 0, and x times M1 plus y times M2 plus z times M3 equals to 0 as well. Now that means we now have 3 equations and 3 variables, x plus y plus z equals to 0, and these 2 equations. Now what we'll do, let's use the equations. Now we have these 3 equations. So first we're going to take the help of equation 2 and 3 to find out the value of x and y. So we need to solve. So solving equation 2 and 3. So how do we solve it? So here we can use the rule of Saros to find out the value of x, y, z. So what we'll do, we'll start with equation number 1. First we will consider the coefficient of y here. So that will be L2, only the coefficient of y. Then moving on, we will go to the coefficient of z. So that's L3. Then we come back to coefficient of x, which is L1, and then end with coefficient of y. So that's L2. Similarly, we will consider the coefficients of x, y, and z from equation number 3. So we'll start with coefficient of y. So that's going to be M2, followed by coefficient of z. So that's M3. Coming back to x, we have M1, and then end with the coefficient of y. So that's M2. Now what we'll do, we'll have to perform cross multiplication. Solving this particular section is going to give us the value for x. Then the next section is going to give us the value of y, and the next section is going to give us the value for z. So that means we have x divided by, so here we have L2 times M3. We're cross multiplying L2 with M3 and subtracting M2 times L3. So we're M2 times L3. This will be equals to y over, so here we have to consider ratio. Now we have L3 times M1 cross multiplying L3 with M1 minus cross multiplying L1 with M3, L1 times M3. This will be equals to z over L1 times M2 minus L2 times M1. Now, since these are ratio, let us suppose that these ratios are equal to some scalar lambda, which means that X is going to be L2 M3 minus M2 L3 whole multiplied to lambda. Y will be equals to L3 M1 minus L1 M3 whole multiplied to lambda, and then Z value will be equals to L1 M2 minus L2 M1 whole multiplied to lambda. Now we have the value of x, y, z, but that's in terms of lambda. So what we'll do, we'll take this and substitute back in equation number 1. Now that means equation number 1 is going to keep on L2 times M3 minus M2 times L3. This is the value of x times lambda added to L3 times M1 minus L1 times M3 times lambda, and then we have the z value given by L1 times M2 minus L2 times M1 multiplied to lambda equals to 0. Now we can factor out the lambda. So this is going to give us L2 M3 minus M2 L3 added to L3 M1 minus L1 M3 plus L1 M2 minus L2 M1 equals to 0. Furthermore, we can rewrite it as 1 multiplied to L2 M3 minus M2 L3. Now here what we'll do, we'll take negative 1 as the common factor. That's that negative 1 gets multiplied to L1 M3 minus L3 M1 added to 1 times L1 M2 minus L2 M1. That will be equals to 0. Now what we have here is 1 multiplied to the 2 by 2 determinant, where we have L2 L3 in the first row and M2 M3 in the second row, minus 1 times we have another 2 by 2 determinant with L1 L3 in the first row and M1 M3 in the second row. Then we have plus 1 times another 2 by 2 determinant with L1 L3 in the first row and M1 M2 in the second row. This will be equals to 0, and this is nothing but, if we combine all three determinants, 2 by 2 determinant, this is going to give us the 3 by 3 determinant with 1 as the entries in the first row. In the second row we're going to get the entries L1 L2 L3, and then in the third row we have the entries M1 M2 M3. So this is the determinant which is going to be equals to 0. So we have successfully proved the problem. Now let's again read the problem once. So if A and B are two non-collinear vectors, we need to show that the points with position vector L1 A vector plus M2 M1 B vector and the remaining two vectors are collinear if this particular criterion is met. So what we did was, we already assumed that these three vectors are collinear and we showed that the determinant equals to 0. So we have successfully proved the problem.